Hello and welcome back to the Dragonfly Daily, your daily source of fresh content on tackling the problems of scientific imaging. I am your host, Mike Marsh, the product manager of Dragonfly. You can follow me at Dragonfly Wizard on Twitter. You can be sure and check out our YouTube channel where you can see more videos like this, but also other videos about how to take advantage of features in Dragonfly. You can also connect with me on LinkedIn or ResearchGate. Today's lesson in the Dragonfly Daily series is Lesson 18, Super Resolution with Deep Learning. If you're watching on YouTube, hit the subscribe button, and if you like content on deep learning, hit the like button. I am nowhere close to the 500 likes I want on my deep learning, so we may not be doing much more deep learning content. If you're watching this live, go later and hit the YouTube site. Watch a few minutes of the video, let YouTube know you like it with a thumbs up. I need those so I can convince the boss that I can keep doing these videos. So as we've talked about this week, we are doing deep learning all week. Lessons 15 started with the background information. Then we looked at some denoising and some image segmentation. In both of those lessons, we only used one neural network architecture or one type of model, which was UNet. Today, we're going to talk about super resolution with deep learning. We will talk about at least one, well, actually two other model types that you could use with Dragonfly besides UNet. You will find that there is no restriction on the type of models you use with deep learning in Dragonfly. You can use models that we've prepared and shipped, or if you have any deep learning expertise, you can design and import your own models. It is completely unlimited. And then tomorrow, we will turn our attention to advanced topics, and we'll talk a little bit about importing, as an example, importing other deep learning models. So, Lesson 18, Super Resolution with Deep Learning. As always, this is using Dragonfly 4.1 with the slightly customized version as described in Lesson 6, Customizing Dragonfly. So the topic is Super Resolution with Deep Learning. Now, super resolution can mean different things to different people. We're not using any optical methods like structured illumination. We're not doing any physics here. We're simply doing image processing like everything else we do in Dragonfly. So with image processing, is it possible to capture higher resolution detail than what you saw in the image? Now, physicists will tell you no, but empirically you can make the case that there should be possible to capture higher resolution information if you extend certain constraints. So if you have built a model that says, I know that sandstone grains have this characteristic shape, so when I see fuzzy images of sandstone grains, I know that they should actually look like sharpened image of sandstone grains. That sort of model with those constraints would not work on other data. So the idea here is if you train a deep learning model under a constrained situation, you might have the expectation that you can recover high resolution information. Now, I'm going to make the case, well, I'm not really going to make the case, but I am going to raise some doubts about how much you can do with super resolution in 3D, and I think there's a lot of room for further experimentation. But I do think it is very strong in 2D, and we can talk about that some more. What we're looking at on this slide, on the left panel, is a low-resolution 3D reconstruction. My colleagues imaged this on the X-Radia Versa at McGill University. It's a micro-CT reconstruction in 3D of a KitKat chocolate bar. And there are different phases in the KitKat chocolate bar. It seems quite orderly on this microstructure. Sorry, I don't have any scale bars. We're not really microscopists. We just write code, and so we often forget to put on scale bars. The image on the left is a low-resolution image. The image in the middle is a high-resolution image of the same field of view. So we reconstructed a low-resolution 3D reconstruction, and then we did a high-resolution interior tomography of the same area. So you do see higher resolution features. So you can see that some of the pores in this chocolate phase are quite blurry, and in the higher resolution image they appear very sharp. Likewise, if you look at this sort of waffle layer that connects the different chocolate layers, it's very sharp in the high-res image and very blurry in the low-res image. And this does dovetail nicely with the question we got yesterday. Can you use deep learning to sharpen images? And so I submit that yes, you can with super resolution techniques. So as I say, the image on the left is the low resolution image. The image in the middle is a high resolution image. The image on the right is a super resolution image that has been reconstructed from the low resolution image based on training data with a high resolution image. So the idea here is you can take images like this and sharpen them to images like this, which means when you encounter pores in your low res image look like this, they can be sharpened to look like this. Will you lose features? And that's really debatable. I encourage you to look at the literature. There is a lot of literature, and the papers are quite nice, and they use a lot of metrics telling you what is lost and what is gained and comparing different resolution recovery methods. So the idea is taking a low-res image, trying to recover high-resolution information details, and this panel just shows you sort of what it looks like, at least on the seam, the difference between the high-resolution image and the super-resolution image. Now, what we will look at today is we'll look at some sample data. There's a Dragonfly sample data set called KitKat. There's a low res and a high res. You can just choose the low res image there on the Dragonfly sample data sets. If you just go to Google and you type Dragonfly sample data sets, it'll point you directly to that page and you can find the KitKat data and download. The other data we'll look at is from the Digital Rocks portal. This is an example of a super resolution white paper, or maybe it was a peer-reviewed paper that was published last year. It was then followed up with another paper that I'm sure was peer-reviewed, where I think it's Ying-Da Wang in Ryan Armstrong's group at the University of New South Wales have looked at super resolution specifically for digital rocks applications. And they've looked and created models using super resolution models that can work on both sandstones and carbonates. So in this case, they're working both on rocks, but they have one model that can be trained on a general data set and work on both. So I encourage you to look at that paper. You can find the paper and the data at the Digital Rocks site. I think maybe I should take you there now so you don't get confused and go to the wrong page. If we go to Digital Rocks portal, I mistyped it, but that's okay. Digital Rocks portal and go to Browse Projects. You will find two different entries with Ying-Da Wang's name. We're not going to look at this one today. This is the follow-up that has some more information. I am referring instead to this project. And here in this project, you will find 6.7 gigabytes of data. The data that we're looking at today, I think, is the DRSRD1 2D data set. So it looks like the whole thing is zipped. So maybe you can download that 4.7 gigabyte data file if you don't want to download the whole 6.67 gigabyte data file. And I refer you to this paper, which is quite useful and describes not only the models that we're using today, but other models. And then you could also check out this follow-up paper that was published last fall in Journal of Petroleum Science. So what we will do is we'll return to Dragonfly. I'll return to my slides. So we will look at the KitKat. We'll look at sandstones and carbonate. And the KitKat, I'll be using a UNet model. The sandstones and carbonates in Ryan's paper, they are using multiple models, and we simply reproduce the WDSR-A and WDSR-B models because those are the ones that the paper concluded were quite strong. Then I will finally talk about another model called DenseNet, and we apply it to KitKat. I'm not going to do a demo of that today. This is using the super resolution wizard that ships in Dragonfly 2020.1. When you use this, you don't have to do any of the deep trainer tools where you set up all of your training parameters and you set up your inputs and outputs. This is streamlined for you with the super resolution wizard. So I won't be demoing that, but I will show you some slides and show you sort of what it looks like. And again, I think there's some caveats when you try and apply this in 3D to 3D data. Finally, I do want to say we do want to collaborate. We think there's a lot of potential on super resolution specifically for 2D applications. This could be geological materials or semiconductor materials, really anything that you look at where you're interested in getting high resolution on a large area. It could also be biological materials of stained tissue embedded samples. Stained embedded tissue samples. So if you do SEM imaging or light microscope imaging and you have a microscope and you're capable of collecting the same field of view at different magnifications, we're interested in collaborating with you. If that interests you, we're happy to work with you. Just email collaborate@theobjects.com. Now, the super resolution for digital rocks, we're gonna do that, talk about that in just a minute. I'm gonna start with the KitKat example. What I will do is I will reset my environment, and I have the KitKat data set that I referred you to on the website. So I just have one slice loaded, and you can see this low resolution information. If I go to segment and I choose segment with classifier, if I select the image, then I can choose from all of the available models that I have in my deep learning toolbox, so to speak. And I have a model here called UNet Super KitKat. So this is a super resolution model in the architecture UNet that was specifically trained on the KitKat data set. So in this case, we had the low resolution image and the high resolution image. We set that up as the pair, ran the training, and we have the model. So if you run a preview in this mode, it will preview on the current field of view. It must first load the model onto the graphics card, then pass the pixels in and get the pixels out. So if we zoom out, we can see the effect of this model. So you do get the idea right away that the areas of the waffle area are sharpened. You also have sharpening of the areas inside the chocolate. So you can see the sharpened model versus what was there before. So is it making mistakes? I don't think it's going to give you 100% recovery of what you would have in the high resolution data. That's certainly not to be expected. And it's also problematic because the micro CT image we're looking at, each slice is not a 2D observation. Instead, it has a point spread function with what is observed in the subsequent and preceding slices. And that's why I think there are some problems that need more exploration, some problems when you try and use super resolution in 3D. I can zoom out to a larger area, run another preview, and we can look at the comparison again. So you can see how much sharper the image is compared to the input image. So if you're trying to do high resolution surface details, or you're trying to understand what is the shape of the pores, you might have something to gain by this. Details inside the matrix, I don't think you'll have as high a fidelity reconstruction. So this model was trained with UNet in, oops, I clicked the wrong button, with UNet in Dragonfly's deep learning tool. Now, we don't have a tool in Dragonfly 4.1 that allows you to create a model that has a different scale input and output. So for example, if we want super resolution and we want to do 4x scale up, then we would need something that would take a 100 by 100 pixel image as input and output a 400 by 400 pixel image. So we don't have a tool in Dragonfly 4.1 that allows you to create that model. If you are interested in doing this, we can simply send you by email something you can drop in Dragonfly that will extend this list so you also have the WDSR, which is a type of super resolution model. Or for that matter, we could, I think my colleague will post on Infinite Toolbox later today, a UNet model that is a super resolution UNet model. So I don't have the ability for you to do this right now with the Dragonfly 4.1 out of the box, but we can ship you existing models and you can use them either for training or for inference. Now, that was the example with the KitKat on a UNet. Now, the other data set I have is the data set that Ryan's group from New South Wales posted on their On Digital Rocks portal. So I'm gonna go to import image files, I'm gonna go to add, and I'm gonna pull in these images. So I don't remember what file format these are. They are PNG. So I don't think we've ever imported PNG files in Dragonfly. I will draw your attention to this. If you import an image that is encoded as a color image, now these images in fact are grayscale, but the PNG format doesn't natively encode grayscale, so it actually is encoding the grayscale intensity in the red channel, the green channel, and the blue channel. So the image is technically encoded as 3 channels. If you import with the default option, you'll have 3 image channels, the red, the green, and the blue, but they're completely redundant. So I'm just going to tell it to import 1 grayscale channel. So now I have that imported, and I will turn the visibility off on this, and I'll just scroll to another slice, click this image, and hit the reset button. So here are some slices of data. They're sort of shuffled, and there are some carbonates, and there are some sandstones here in this example. So what we'll do is we will look at another model. In this case, we're going to look at the WDSR model. This one is called WDSR-A, and we can do a preview. So again, it has to load the image, and then it has to load the model and then execute. This image that you see on screen is only 200 by 200 pixels, so it actually runs quite quickly. So if we look at what the data looks like before the super resolution, it looks like this. After the super resolution, it looks like this. If we advance to another slice, in this case, it's a carbonate, I can click the preview button, and you can see the effect of the super resolution on the carbonate. So it's sharpening the carbonates and the sandstones. Now, I trained this model in Dragonfly using the WDSR model. So if I gave you the same input data that Ryan used in his paper, and all of those data are on the Digital Rocks portal, you can go in and use my WDSR model. You can see the architecture looks very different from a UNet. You can go to training, and you can plug in Ryan's downsampled images and upsampled images as input and output, and you can initiate training. Now, this model, we could put it in the Infinite Toolbox. We can actually, I think I mentioned earlier, we can actually send you a piece of code where you could it would just add directly on the new page. So if we send you that piece of code, then in the dropdown, you'll see not only autoencoder and FC-DenseNet, etc. You'll also see WDSR-A. Now, I want to go back to the slides. So this is a look at one of the figures from that paper, and they are evaluating the high-res image versus the low-res image versus different interpolation methods, including the WDSR-B and WDSR-A. They evaluate multiple super resolution models, and you can draw your attention to that paper and try and decide for yourself what you think of those different super resolution models. Now, I also want to talk briefly about another model. This is described in a paper in 2018, Can Deep Learning Relax Endomicroscopy Hardware Miniaturization Requirements? This paper is available also online at archive.org. And again, they are doing a treatment and showing the original data set, showing what super resolution looks like with conventional methods such as nearest interpolation and bilinear interpolation versus their dense net interpolation. I'm showing this data because this is what's implemented as the default in the super resolution wizard coming out in Dragonfly 2020.1. In this case, we're now looking at KitKat data that has been processed with the super resolution wizard, and the figures are not really optimized for the presentation. I just pulled them from our notes files. When my colleague was doing some super resolution testing, he just captured some figures and put them in our notes pages so we could refer to them later. They weren't actually ever intended for presentation, but I wanted to share them with you right now. So what you're looking at is a low resolution area in the sort of waffle phase, what the high resolution, corresponding high resolution area looks like, and what the sharpening looks like. Now, if we go to another slide, here we're on the same chocolate sample, but now we're looking sort of in the chocolate matrix. Here we're looking at another area where you can see sort of some chocolate matrix and some waffle matrix. So you will see that, you know, it reconstructs the image sharply, but maybe it's not getting the right shape. And that I again say is a problem because the image here is actually a convolution of what's happening in the slices before and after it. And so you are sort of limited by the physics of the experiment in 3D. So we could talk more about that offline, but you do see that you get some very nice sharpening. So consider, for example, what this looks like compared to this, or even what these pores up here look like in the low-res image compared to the structure resolution recovered image versus the high-res image. All right, that is all I was going to show you today on the topic of super resolution. So I am going to turn now to questions and answers. And Benjamin, if you're online, I may unmute you in case people have questions where I want to refer to you. So let me pull up my participants panel. Benjamin is already capable of, well, I'll just unmute him. Benjamin, you're unmuted. I think you can probably mute and unmute yourself at this point. The first question is, can we use high resolution image of a small zoomed part of an object obtained by scout and zoom option in Zeiss microscopy to sharpen the image of the object when acquired with lower resolution? Yes, you can. That is exactly the sort of thing you can do. So if you have a microscope such as the Zeiss X-Radia Versa or X-Radia Ultra, or really any microscope that can do interior tomography or what some people call ROI tomography, then yes, you can capture both images. And so what I submit the experiment you should do is image a large field of view at what you might call scout mode, then zoom in on at least 2 different areas, then use one area for training and leave the other area specifically as a validation, or even do it with 3 data sets so that you can train, validate, and then you can run your model on the 3rd data set and have a ground truth to compare. So absolutely, that's a great way of using super resolution. Next question, is deep learning part of the, oh, I already answered that. Yes, deep learning is included with the non-commercial release. Next question is, when I'm trying to register on Dragonfly forums, I have this message, sorry, registration is currently disabled. Thank you for the question, Paul. The registration online is not permitted. The only way you can register is from inside the Dragonfly user interface. If we change the web page and allow you to register online, for some reason, people in different parts of the world will just create accounts with robots and fill the forums with pornography. So we can't allow open registration. I don't know why it's such a problem, but you can register from the Dragonfly user interface. You'll find it in the tools menu. Sorry, not in the tools menu. It is, let me close this and go to help and do request write access to Dragonfly forums. So that's where you want to go. And if you lose your password, you can recover your credentials with that option. Next question. Previously, you mentioned that training paired data requires 2 data sets of the same size. In the case of training low and high resolution data like the KitKat, I'm assuming the high resolution images have more pixels than the low resolution. That is absolutely correct. And so we've actually made an architecture change between Dragonfly 3.6 and Dragonfly 4.1 that permitted you to have deep learning models that have different input sizes. So it will be specifically encoded in the model. So if you have a UNet model that is set up for super resolution, then it will only let you pair data that have the appropriate pixel size difference or matrix size difference. So the next question is, Can you do this across modalities? Use an SEM image to sharpen a CT image. You can, and I expect it would give good results unless you have very different imaging contrast from the electrons than you have from the X-rays. So we've talked about doing this on some carbonate samples in the past, but yes, this holds a lot of potential for sharpening CT images. Next question is, do you change the voxel resolution too? Does the image size change? Well, that's actually a good question, and the answer is yes. So if I run I've been using the preview, if I actually hit the segment button, I know this is not segmentation, this is super resolution, and this language will be easier to follow in the next release. But whether your model is denoising or segmentation or super resolution, it's always this one button right now, just marked segment. So I've been clicking preview today. If I clicked segment, it would apply this model to the entire stack of, I don't know, 200 slices, which are all 200 by 200 pixels. The output would be 200 slices, and they would all be 800 by 800 pixels, because this super resolution model is a 4x scale, and it would be ×4 in X and ×4 in Y. Okay, the next question is, can you walk through how to set ROIs and creation of the training data for this type of application? Well, that's a good question, but you don't actually need to use any ROIs at all. This is more of a regression type model. So just like the denoising models we looked at, you don't need ROIs or multi-ROIs. You're just training from grayscale pixels to grayscale pixels. Just in this case, it's from low-res grayscale pixels to high-res grayscale pixels. The next question is, you mentioned the problem in 3D where the nearest slices affect the resolution. For FIBSEM type 3D data, where the slice data is chosen, it can lead to reconstruction of a sphere into an oval type. Can you use artificial intelligence to help recover the real morphology? Reconstruction of a sphere into an oval. If I am cutting through a spherical grain with a FIB and I collect images and my images are properly aligned, it should still reconstruct as a sphere. So I'm not sure why it would show up as an oval. So I think my problem is I don't follow your question. If you want to ask again, I'll look at your question, but I don't understand currently. Next question is this similar to the last two questions? Can I use Dragonfly for multi-scale registration of high-low res images? So you can use Dragonfly for registration, and we covered that a little bit in the 3D stitching lesson, which I think was lesson 9. In that lesson, we looked at stitching 3D datasets. I don't think I mentioned you can stitch datasets of different scale or different pixel size, or maybe I should say different magnification, but you can. But more importantly, you can use the registration tools that I showed in lesson 9, 3D stitching. You can use those registration tools to register a micro CT and a FIBSEM. Now, if you want to register a 2D SEM to a 3D micro CT dataset, you can use the same tools, but it's a much harder task. You really need a guide that tells you where to initially position a 2D SEM image if you're trying to position and register a 2D SEM to a 3D micro CT. That would be a very good demo or webinar. And if you have those data, a 2D SEM and a corresponding 3D micro CT, or if you want to collect those data, we could collaborate and I could set up a demo on that specific topic. Next question, are you aware of any training data set for soft tissue anatomy of vertebrates? For example, micro MRI or iodine stain CT. I am not aware of those. So I suppose you're looking now not for super resolution, but for segmentation. And so if you have the trained data, yeah, that would be amazing if you could somehow image an animal without stain and then with stain and have the animal be in exactly the same position with no deformations. If you could somehow do that, then you could use the stain to do a very high quality segmentation and use it as your training target for a segmentation model. I'm not sure if that's the direction you're going, but I'm not a good reference. If anyone else knows an answer to Aki's question about training data sets for soft tissue anatomy, you can reply directly to Aki's question here in the text. Next question, how can I measure the accuracy of the model in order to report it? Well, I don't really have the time to get into the scope of that, and I'm not really the right person to ask. But you can look at the papers I referenced, and they show how they report the accuracy. There are different metrics that you can use for comparing the super res reconstructed image to a ground truth high res image. So I would look at those measures and sort of look at the literature. And if you have questions after that, you can email us. My colleague Benjamin Benjamin's already put an answer. You can compute the mean squared error, or the, I don't know what P in PSNR, it's a signal to noise ratio, or SSIM metrics. Thank you, Benjamin. The next question is, since this is increasing the voxel size, should this be done on a smaller sample? For instance, in a stack of 1,000 slices, should you pick only a subsample? Well, it does increase the file size, and it increases the file size, at least with the current methods, as a square factor. So if you do super resolution 2x, then your file size will be 4 times larger. So if you don't have the memory or the hard disk space is not going to be an issue, but if you don't have the memory to handle data that are going to be 4 times larger, then you should stick with working with smaller input data sets. Next question is, why does it look like the super resolution treatment reduces the noise and increases the contrast as well as improving the resolution? Wow, that's a really good question. Benjamin, have you thought about that? It's, in some of our figures, it looks like the contrast to noise gets better in addition to the image being sharpened. And I think that's quite clear in images like this, and even in some of the other slides. Here it looks much less noisy. Benjamin, do you have any insight into why?
Not really, but it's like the noise models also. The models are not able to learn the noise, so this is why it's denoising. But for the contrast, I'm not sure why it's happening.
Yeah, that's a good point. So because the architecture of the neural network is not good, in these symmetric unit style networks, there's a compression and a decompression, and it happens through, I guess, maybe pooling layers in the network, but the compression is not able to encode the noise, and so when it gets decompressed, the noise does not come back. So that happens in denoising models, as well as, well, really any grayscale regression models, including these super resolution models. So the next question, let's see, and how similar do data sets need to be for deep learning model trained with one data set to be effective on the other data set? We don't have a statistical answer to that question, but if you're imaging on the same microscope with the same imaging conditions, so if it's X-ray CT and you're imaging samples that are the same size and with the same beam energy and exposure times, then I expect you to have success. So Sydney commented on this in one of the earlier lessons, that they had data sets with different brightness and contrast, and they had to normalize the histogram before they're able to use the same model. So in some cases, if you don't have the same imaging conditions, you could just massage the input data. So that's an option. The next question is, so Aki comes back and clarifies, I was asking about the data set we use for super resolution. I have iodine stained samples of vertebrates and curious whether super resolution can be applied to increase distinction among various soft tissue structures. I'm not sure if super resolution is an appropriate application for vertebrate anatomy. Well, we'd be happy to look at it with you or collaborate with you. I don't have any particular insight on whether super resolution is going to work. I don't really know anything about the iodine staining protocols for soft tissue and what's involved in them, and how that would change, or how that would change the likely success or failure of super resolution methods. But we're interested in looking at the data with you. And I think I've got one question left. Can we save the result to disk and not have the whole new data into memory? We do not have that capability. We've never added the, yeah, the answer is no. It could be added. It could, if there were actually use cases where people were running out of system memory, it could be added where as every slice is processed, it was then output to disk and not kept in memory, but we don't have that built into the software right now. If you actually have cases where you're doing this, or have cases you can't run the super resolution. Because it won't fit in memory, let us know, and we'll use that as a test case, and we'll build that into the software. Well, that's all the questions. So thank you all for your questions. Thank you all for your attention. Tomorrow, we're going to do some more advanced topics and look at a little bit of the other things you can do to tune and fine tune your models and how you can put custom models in Dragonfly. I think I'll talk briefly about instance segmentation. There's all sorts of things that we'll talk about tomorrow to sort of cap off this week on deep learning. So as always, thank you for your time. Thank you for your attention. Look forward to seeing you tomorrow. Stay healthy and have a good week, everybody. Talk to you tomorrow.